Welcome back to the last topic in Unit H. Today we're going to cover H5, proving the theory of conservation of mass. You can follow along on pages 80 and 81 in your textbook if you'd like to. So, in our last lesson we talked about the theory of the conservation of mass, and let's just state it once again for everyone so we can all remember. The theory of the conservation of mass states that mass is never created or destroyed. And specifically we talked about how mass is never created or destroyed in a chemical reaction. But since this is such an important theory, we should take some time to review and to try to prove that this theory actually holds true, because we're claiming that it's a theory that has no exceptions whatsoever. So it's pretty important that we're able to prove it, able to convince ourselves that it does in fact hold true in every situation. So one way that we can begin to gather some evidence for the theory of the conservation of mass is by looking at the reaction of magnesium as it burns in air. So before we do anything else, we want to remind ourselves of the word equation when magnesium burns. And if we remember, it's magnesium plus oxygen goes to make magnesium oxide. And so if the theory of conservation of mass holds true, then the mass of the reactants, which is the magnesium plus oxygen, should equal the mass of the products, which is the magnesium oxide. So you can imagine if we measure out a certain amount of magnesium, burn it in air, then we should be able to see an increase in mass between the magnesium and the magnesium oxide, because the magnesium will join together with oxygen molecules from the air. And so we can in fact set up such an experiment. If we look at our picture up here at the top, in step 1 we take it's a ceramic apparatus. We call it a crucible. It's just a little bowl called a crucible. It's made out of ceramic. It's good for burning things. And we need a lid on top, which I'll talk about in a second. And we weigh all of that together, just an empty crucible, and we get 50 grams. Then we throw in a piece of magnesium ribbon into our crucible, remeasure it, and we get 51.2 grams. So how much does our magnesium weigh? Right, 1.2 grams. Good. So then we burn our magnesium, like we said we were going to. And this is where this experiment gets a little bit tricky, because when we burn the magnesium, some smoke gets produced, and the smoke actually contains magnesium oxide, which is the product that we want to keep around. So that's why we have to keep the lid on the crucible the whole time. But remember that we're also hoping that the magnesium will react with oxygen from the air, so we'll also need to open the lid carefully every few minutes during the experiment to make sure that our magnesium has enough oxygen to react with. So then once you've completely burned your magnesium and you see a white powder left in the bottom, magnesium oxide is a white powder, then you remove the crucible from the heat. We go to step 4, we allow it to cool. This can take a while. Crucibles stay pretty hot, and we'll do this demonstration in class, by the way, so you guys will get to see this. And then step 5 is, of course, we want to see if we actually gained mass from the oxygen in the air. So we go back to our balance. We now put the crucible and the lid and all of the white powder that we have back on the balance. In this example we get 52 grams. So if we compare 52 grams, which is the mass of our products, to the mass of our reactants, which was 51.2 grams, we see that we indeed did have an increase in mass between reactants and products, meaning that the magnesium must have joined with oxygen molecules from the air. So to do a little analysis of this experiment, we now want to calculate the mass of oxygen that joined to the magnesium during the reaction. So how are we going to do this? Maybe some of you are already a couple steps ahead of me and already have the answer, but if we want to calculate how much oxygen joined to the magnesium during the reaction, we're going to want to subtract the starting mass, right, before any reaction happened, before any oxygen was joined. We want to subtract that initial mass from our final mass after we added the oxygen, right, after the oxygen joined with the magnesium. So then it becomes a pretty simple arithmetic problem once we realize what we want to do. So 52 minus 51.2 gives us 0.8 grams. So if we calculate the mass of the oxygen here, we get 52 minus 51.2 equals 0.8 grams of oxygen. And that's our final answer. Let's throw it in bold. Perfect. So I hope you guys could follow along with that explanation of that experiment. And if it seems a little bit hazy, make sure you pay attention, because I'll do this demo in class for us as well. Alright, so let's say we just did this experiment one time. We got 0.8 grams of oxygen as how much oxygen we added. We've been talking a lot this year about how to know if we can trust our results, right? How do we know if this 0.8 grams of oxygen is really a reliable result? Maybe there was a fluke, maybe I let too much smoke out of my crucible, maybe I didn't let enough oxygen into my crucible, so on and so forth. So we'd want a way to corroborate or to check if our results were reliable. And so to check the reliability of an experiment, what we can do is carry out the experiment a bunch of different times using different amounts of magnesium. So you can imagine if I started with a small amount of magnesium, I wouldn't get that much oxygen to join. If I started with a bunch of magnesium, there'd be more oxygen needed in order to burn all the magnesium up, so I'd get more oxygen joined. So if we do this experiment for a bunch of different masses of magnesium, and then if our results form a pattern, then we know that our results must be reliable, right? Because that pattern tells us that the magnesium and the oxygen are reacting in a similar fashion in every experiment. So this data table that you see here is directly off of page 81 in your textbook. So if you want to be following along with page 81, and so this looks like a bunch of numbers, right? And we want to be able to know if there's actually a pattern amongst these numbers. And so what we're going to do, and in your book asks you this, question D on page 81 asks if you can draw a scatter graph to show these results. And in fact, drawing a scatter graph is going to be able to show us if we have a pattern or not. Because it's hard to tell, looking at all these numbers, if we actually see a pattern, if we actually have reliable data. So an easy and quick way to plot a scatter graph is to use Microsoft Excel. So if you look here on the left, I've just copied down exactly what the data on page 81 contains, and I've then what you can do is you can highlight the data that you're interested in and insert a chart in Excel. You can go to Insert and then click on Chart, and what it produces looks something like this chart that I've made here. So I put massive magnesium burnt on the x-axis because that's the variable that we are changing ourselves, right? We're deciding how much magnesium to burn. And so then the dependent variable is the mass of oxide produced, which goes on the y-axis because that's the one that we're interested in measuring. That's the one that we aren't sure about. So if indeed we look at our data points here, we see that they do form a pretty nice pattern. There's one point that's a little bit out of line, but that's expected when you have experimental data. It'll never be a perfect line, but you can see that there's definitely a pattern there. There's definitely a trend. So we can therefore conclude that our results are fairly reliable, and this gives evidence to support the theory of the conservation of mass. And so let's just now talk about one famous experiment from the 1700s, which was actually the first to prove that the theory of conservation was indeed correct. And so these three pictures, these three figures, are also in your textbook on page 81. but I want to just take you guys through step by step because it can be a little bit hard to follow along with the pictures in the book. So I want to give a thorough explanation of what this experiment was all about. So it was a scientist whose name was Lavoisier, who obviously with that name he was French, and like I said, he worked in the 1700s, and he was setting out to prove that the theory of conservation of mass was correct. So step one, as you can see in the figure, well, first of all, let's talk about the experimental setup. So he has this flask on the left, and then he has a bell jar on the right that can fill either with air or with mercury or whatever. So first step was to heat the mercury. When mercury burns, just like when magnesium burns and makes magnesium oxide, when mercury burns, we get mercury oxide. And instead of a white powder, mercury oxide is a red powder. So indeed, when Lavoisier heated the mercury, he saw a red powder formed, which was mercury oxide. But that oxygen had to come from somewhere, right? So the oxygen was actually sucked out of the bell jar, and that's why on the right side you see the magnesium level has risen, because there's less oxygen in the bell jar, because that oxygen had to go to make the mercury oxide, or the red powder. And then to prove that what he in fact trapped in that red powder was oxygen, he isolated, or he took out just the red powder from step 2 and put that red powder into a clean flask in step 3, and then he heated that to release the oxygen from the mercury, and because he wasn't sure if there was actually oxygen there, so he heated it to see if he could release the oxygen from the mercury, and in fact, as he burnt the magnesium oxide powder, he turned magnesium oxide back into mercury, released the oxygen into the bell jar, and the amount of air in the bell jar gradually increased, proving that he had in fact trapped oxygen with his mercury oxide, which proved that the theory of conservation of mass was correct. Alright, so let's give a quick recap. We had a pretty dense lesson, even though it was only on 3 slides. So we first talked about how we can gather some evidence for the theory of conservation of mass. We talked about burning magnesium in a crucible, and then seeing if we can get a mass change when oxygen joins to the magnesium. And in fact, we saw in this example that we got a mass change of 0.8, so we must have added 0.8 grams of oxygen to our magnesium through burning. Very good. And then we said, well, how do we know if that 0.8 grams is worth anything, if it's actually a real value, if it was just a fluke? So what we can do is we can set up a series of experiments where we use a bunch of different masses of magnesium, and we see if the pattern holds. We see if we have similar amounts of oxide proportional to how much magnesium we burn. And as we looked at using Microsoft Excel, our results do in fact form a nice pattern in a scatter plot, right? So if I blow this up, we see that we have our data points more or less in a line, telling us that our results were reliable. And then finally we talked about how the French scientist Lavoisier proved the theory of conservation of mass in 1775 by first heating mercury to produce mercury oxide, which used up oxygen in the bell jar. Then he isolated that red powder and burned it, which released the oxygen again, and the bell jar slowly increased with air, meaning that in fact the oxygen had been trapped by the mercury oxide and no mass had been created or destroyed in this entire experiment. So perfect, thanks for hanging in there through that rather dense lecture, and great work on finishing Unit H, and good luck on your exam, and we'll see you back for our next unit, which is to be determined, and otherwise, thanks.